starting with a simple Jupyter Notebook example, which shows you how to access the data on WEkEO programmatically. So this is building on what I explained to you yesterday. From the viewer, you can find the information that's necessary to execute what we call an API query to our Harmonized Data Access API that we have in WEkEO. And I'm going to show you how you would do this through the medium of a small Python script in a Jupyter Notebook. And we'll be doing that in the WEkEO system. So by all means, if you'd like to try and follow along, please do. But don't feel any pressure. Like I say, you'll have the recordings of these sessions to go back through in more detail. Sometimes it can take a couple of times, takes some time to get familiar with all these different processes we're introducing you to. But we're also open to following up with you after this. You're very welcome to contact the WEkEO support, and then they will forward on questions to us if you need help with working with any of these notebooks and tools. Okay, so I'm now going to share my screen. Just give me a second and we will start back at the WEkEO portal. So this should be quite familiar with you by now. So you should be used to seeing this interface. I'm already signed in, but you don't necessarily need to be to access the first thing I'm going to show you. The first thing that I'm going to show you is actually our Jupyter Notebook catalog. So this is slightly different to the order that was in the advertised agenda today, but I think this will be quite useful for you still to see. Okay, and making sure I can still see my screen share. Perfect. Okay, so if you're on the main website, you can find the notebook portal just by scrolling down here, and you'll see it's advertised in this very nice little design here that actually looks like a cell of a Jupyter Notebook. If you click Get Started Now, and you'll come to this catalog, which is our Jupyter Notebook catalog. This is quite a new thing that we've recently put onto WEkEO. So if you've got any feedback and questions about it, we'd love to hear from you. We're trying to develop it, so you might find some bugs here or there, but hopefully you'll see it improve and the catalog grow with time. And the idea of this catalog is to allow you to explore the notebooks that we're able to provide for training and user support in a more interactive way, so you can see what's in them before you have to download them or git clone them, or install any Python, or even have access really to the WEkEO Jupyter Hub. This allows you to see, is this something I'm interested in pursuing beforehand? The notebooks are organized according to the different thematics, so maybe we can start by having a look under marine. And you can see here, if you scroll down, we have a whole range of different notebooks. They're all summarized in these little cards, which allow you to understand and explore different marine products that are available through WEkEO. And some of these notebooks are more technical in nature. They'll tell you about downloading the data. They'll tell you about the areas the data covers, about its format, about things like that. And some of them are more applied. So they'll show you how to visualize some of the imagery. And then some of them, even as we get further down, are more related to specific applications. So if we scroll right down to the bottom here, you'll see this is a notebook relating to the deoxygenation case study I spoke about on day one. Same here with the carbon pools, here for the heat wave. And down the bottom, the tropical cyclone example that I showed you. So you can use this to look through the notebooks. And then by clicking on any of these individual examples, oh, sorry, a bit slow here, throw it down. You can open up the notebook in a more rendered fashion. So this looks like maybe what you saw yesterday when Ben showed you the notebooks, but it's not an interactive rendering. This is just showing you what the notebook looks like. It tells you what's already in it. It's already pre-run, so you can see the output you would expect. And from here, you can then figure out, is this something I'm interested in working with more? Maybe I want to try this for myself, or edit it to apply to a different image or area, or something like that. So it shows you what it looks like. You can then at the top here also launch this in WEkEO already, but I'm not going to do that right now because we're going to move on and look at some of the other things behind the scenes here. But before we go from the catalog, I just wanted to show that we also have some cross-disciplinary themes that are emerging. So all the notebooks under this machine learning tab are cross-thematic. So some of them are atmosphere related, some land, some climate, some ocean. And they all come from our AI for Earth observation MOOC that we ran last year. So I don't know if any of you took part in that, but that material is also in the catalogue here, and you can explore and work with it. And I just then wanted to show you one relevant marine example here. This is an example using machine learning for water type classification. It's more theoretical and basic, teaching you about how this process might work and exploring kind of the relevance of it and where you might need to look at more complex methodology. But it's a really good one if you want to get to know a bit about machine learning and how it works. So just scrolling down here, you can maybe see some of the outputs that come out from the imagery, some more information about the actual signals that are there. And then there's some classification process further down. And this can run and you can do this analysis yourself using this example. But just one final point is that you can also then go from here to our GitHub. So Ben spoke to you about Git yesterday, and we use Git extensively to manage this code base that I'm showing you. It becomes very difficult and very confusing what's happening if you've got lots of people writing code, you've got different versions of it. Being able to track it in something like Git is really important, and it also allows us to have a base where we can share this code from to other places. So to the catalog, for example, directly to you, as you can see here in the GitHub, but also to our Jupyter Hub, which you'll see again in a minute. So here you can just see that we've now opened that notebook in the GitHub, and it does render relatively well here, but it's not as nice as the catalog. So if you want to explore the notebooks thoroughly, I'd recommend looking at the catalog. So now we're on the GitHub set of repositories. This is a group, I think it's called a group in GitHub to speak. So WEkEO has its own GitHub kind of group, and we have various different repositories on here. Now, repository in Git terms is kind of the smallest unit of code that you can share. So you can download a whole repository, or you can clone a repository, as Ben showed you yesterday, and we'll also look at that again in a minute. So just to show you, under our repositories tab here, we have a whole bunch of different repositories of code that you might want to have a look and work with. And I'm going to look at one of these in a minute in the Jupyter Hub directly. But just to give you an idea that these do exist here, if you look at the WEkEO for Oceans, you'll find that we've got various different, they're actually sub-repositories, sub-modules in here. And if you look here, going back to that previous example, you can see some of the ones on the eutrophication and marine heatwave example, the carbon one, they're all actually in this repository as well. So it's the same stuff that you're looking at. This is just kind of the central repository where we keep it all. And if you want to do more advanced usage of code, then learning how to work with this style of presentation of code from Git is quite useful. So I would always recommend doing that. So the second part of my demonstration today is actually going to be based around one of our repositories, which is this WEkEO for Data one, which is kind of, it's a theme agnostic repository in a way. It's mostly to show you how to use the harmonized data access, which is really important for any of the notebooks and examples that we were showing you there. You really have to know how to get the data first before you can do anything with it. So that's this repository. And I just wanted to point out some features of the repository, such as this README, which will give you all the information you need to run the repository, to clone it and to run it on your own computer or in the WEkEO Jupyter environments, or indeed in any of our virtual machine environments, basically anywhere. You can, using this information, take the code and run it anywhere you like. It's relatively easy to do it in the JupyterLab, as you'll see in a minute, because it's already actually there and the environment is already set up. But just to make a point that here you have a clone command, which allows you to then effectively download. It's not really downloading, it is downloading, it's bringing a copy to your computer or wherever you're working, but it's actually creating a link between you, the repository you've got on your computer and this remote collection. So if you wanted, so say I updated this today and you wanted to get a new version of it, you don't need to download a whole new version. You can just say, hey, at my computer, can you go and get the latest version of this and bring it down? And then you don't have lots and lots of copies, you just have this one version controlled set of code. So this is really the strength of Git, and I think it's something you'll come to appreciate as you code more. Maybe some of you already use it and you'll then know how useful it can be. But let's go from here back to the WEkEO portal. And from here, we can go then to the Jupyter Hub. So under my dashboard, because I'm already signed in, I can then access the Jupyter Hub. And if you've got a WEkEO account, you can do this too. We give it a minute, it will load up. Here we are. So what you're actually seeing here is my my instance of the JupyterLab, and you can see there's actually, if you've got yours open, there's some different things in here compared to what you may have. And this is because I've already been working in the JupyterLab, obviously, for some time. So there's some different bits and pieces that I've already brought together. But you'll certainly have this public folder and maybe an old files folder, depending on how long you've been registered for WEkEO. In the public folder, you can see that you actually already have a copy of all of the GitLab repositories that were represented there in the catalog. And this is where you will end up if you click from the catalog to go into this public area. Now, this is a copy of the code that is called read-only. It means that you can execute some of it, but you can't edit it and run it and generate new content here. This is pulled routinely so that you always have a copy that you can access within this environment, but you can't really work here. So if you want to work with this, you've got two options. You can either right click, and if you click cut, it won't actually cut, it will just copy it. And you can then go back into your main working space and right click and paste it. Or you can do a slightly more advanced thing, which you can see actually I've already done here. So I'm just going to close this example. This is what the launcher normally looks like in the JupyterLab. As we showed yesterday, you can launch notebooks, you can launch a console or a terminal. So I'm just going to go back and open a terminal again. If you want to use a more advanced workflow and actually clone your code in, so this could be any of our repositories that I've shared with you in the GitHub, or indeed any repository of code that you found out there on the internet, you can clone in here. You can just run that command. So if you copy this and paste it in here, that, and then run it, what it will do is it will clone the Git repository from that remote GitHub in this case, into your Jupyter environment. Now I've already done this, so I'm not actually going to run this command here right now, because that would give me a new copy of it, which I don't want. But what I am going to do is go into that folder, and then you can see in here there's a brief notebook here, which is a sort of a welcome orientation to the JupyterLab, so you can read through this if you like. But I'm going to skip straight to a notebook, which will allow us to look at the Harmonized Data accessAPI. So I'm going to open that one now, and you can see it's already been run, but I'm actually not going to do that. In fact, I am going to go and reclone, because I just want to make sure I've got a fresh version here for you. So let me just do that quickly, and you'll see what a clone actually looks like. Just give me a second. So you're going to remove that and show you fresh how it works. All right. Okay, so that's then deleted that. So I'm now going to clone it, as I showed you before, using this command here. And you'll see now it's very quick. Code is very, very light, usually in terms of its size. It's quite small, so this allows you to clone it. So if I now go into here, see I've got a fresh version of this notebook from seconds ago, which is already run, but I'm actually going to run it for you now as well. So one thing that's worth bearing in mind, a couple of basic things for operating in the JupyterLab environment, is under kernel here, you can restart and clear outputs. So when you clone, our notebooks are already pre-run, but if you want to start running them yourself, you might want to restart and clear them all. This is also something that's quite useful if you're playing around coding and you do something a bit silly and maybe bring in far too much data and you crash the notebook. If you've programmed before, you know this is something that happens relatively commonly. You might want to clear the whole notebook and just start again and just check that you're actually running it through correctly and isolate where the problems are. So it's a useful thing to be able to find and do here. And you can use up here some commands to run all the different cells, but you can also go through them and run them individually. And I would always recommend doing this to start off with, because it allows you to really understand what is going on in each of the individual cells. And there's one of the nice things about Jupyter notebooks is that you do usually get them with all this text around them that explains to you what is going on in the different cells and why you're doing what you're doing. In this way, they're really good for self-paced learning. You don't really need to listen to somebody like me go through this notebook. You can go away and do it yourself. And if I've done my job right and written the notebook nice and clearly, you should be able to follow along with what's going on. But we will go through this one anyway. So we'll start off with importing the different libraries, packages that we need. And you can see those here. And you can see that when I clicked the little play button up here, we got a number that appeared in here. And this means that our notebook has run and there's no errors showing, so it seems to have done what we expected it to do, which is import these different libraries that we wanted to work with. But we're also going to we're going to import one extra package here, which is this HDA client. So normally you might put this up here, but because we want to draw attention to it in this notebook, we've put it down here. So I click there, it should import too. This is installed centrally in the Jupyter Hub environment. So following from what Ben said yesterday, you don't actually need to do much installing and things yourself in this environment. All the packages, libraries that you need to run the notebooks we're sharing with you already exist in this notebook, in this mini WEkEO Lab kernel, which you can see you can access up here. So they already exist. So we've already got the HDA library in there, so we don't actually need to install that ourselves, which is great. We have a question in the chat, which maybe I'll just go back to. So just showing you the actually getting into the Jupyter Hub platform from WEkEO. If you're here in the main WEkEO website, it's under Dashboard and then Jupyter Hub. And if you click on that, it will spin up. So it should be fairly easy to follow from there. If you have any problems, we can help you more in a minute. So going back to the notebook, we've now imported our HDA client, which means we can start working with all the different tools and methods that allows us. You can read through these sections that come up next. It just shows you about searching for data sets on WEkEO. So say you have no idea what you're looking for, the best place to start, as I said yesterday, is in the catalog. So from the catalog, you can search for the data you're interested in. And then from there, you can get the dataset IDs and information that you need to execute a query. Now, you probably only have to do this once or twice when you're looking for new data. After that, you don't necessarily need to go back to view. You can just adapt your queries to find the right time, space, area that you need for the products. But it's a good place to start when you're building a new workflow, is to look from the viewer side first. So in this example notebook, we're working with a Sentinel-3 Ultra Level 1B full resolution product. It has this collection ID, which you can see is in the viewer here. So we can put that in there and we can use that later. But we can also cheat and create a kind of false download in viewer and copy the query, as you'll see in a second. So I'm just going to run that one anyway. One now, where's strange? Going to run this and make sure we're in the right order. So we're now in a 3. The most important thing you need to do to make the API access work is authenticate. So you will all have received a WEkEO login. So if you've registered for one to access the JupyterLab and things, you'll have these a username and password. And this is what allows you to then say, hey, I'm Hayley, I would like to make this download from WEkEO, please. Can you go and get this data for me? You need those credentials in order to authenticate the API. It then goes away and gets some individual access tokens and things like that. But unless you're really into understanding API architecture, this is maybe not so important for you to understand, but this notebook will explain to you a little bit about how it works. The HDA client that we've provided here does actually take care of a lot of this for you. So really all you need to provide, as it says here, is your username and password. And we give you two options for doing this in this notebook. So you can create a credentials file, which has the URL of where the WEkEO HDA access is, and then you need to fill in your username and password. So you can do this and either put it in your home directory. So actually, if you're working on your local computer, you're not in the JupyterLab, you can do this, put it in your home directory. If you're working in a hosted environment like this one, you might want to be a bit more specific and specify exactly where this credentials file is created. If we look back here at home, you can see I've created mine here. So I will actually specify where it is. And that's what this part explains here, is that you actually want to set up your call to the client to point to a specific file containing your information. This can sometimes be useful because you don't always have access to your home or what the computer thinks is the home directory, depending on where you're working. In the case of the JupyterLab here, that's the case. So you want to specify where it is. So I'm actually going to use this line here, and I'm going to copy it now just to show you where I'm going to put it. You could also do it directly. So you can use this command here, and you can write your username and your password directly into a cell in the Jupyter Notebook. Now, this is quite easy to do and quite tempting, but I would recommend you don't do it because it's not very safe. If you share this notebook with somebody else, there's a good chance, and I've done this myself many times, that you leave your credentials in there, which means somebody else can go and use them to do whatever they like. So they can sign into the WEkEO JupyterLab and set up a whole load of crypto mining or something horrible. You don't want that to be the case, really. And we would probably stop your account if that's what happened. So, you keep your password and your username secure by putting them into a configuration file over here. And it's for this reason that I'm not going to show you my configuration file, because you would see my username and password. So I've already preset my configuration file. It's just a basic text file, as I said, with this copied in and my username and password replaced with my particular credentials. So now that I've got that, I can adapt this cell here. And I'm going to paste this in here. Oh, no, sorry, that's not what I want. That's the previous thing I copied. We're going to copy this text. Actually, I think I need to double click on this and copy it from here. Sorry, this is me not being able to cut and paste things properly. There you go. Okay. So now I've put this in here, but I still need to adapt it so that it knows exactly where my file is. So I'm going to put in where it says here, your config file, I'm going to put the path to my config file, which I know is at home/jovian/myconfig.txt. Now, if you name yours the same thing, you can also use exactly this this command that I've shown here to work for you. So this is this one. You can also look and see where it is under the path. So that's quite helpful, or under here, it will tell you as well. So let me just run that. And you can see again, it's completed. So it's happily recognized that my file is correct. If my file was not appropriate, so if I'd put something in that didn't make sense, if I'd forgotten my username or my password, it would say the client has built-in functionality to tell you whether things are working or not. So that's quite useful. It's designed to help it be more user-friendly for you. So the next thing we're going to do is we're actually going to load one of these data descriptor files. So I mentioned the idea of a JSON file yesterday. It's that thing you saw, looks a bit like this in the viewer. And you can write these yourself, or as I said, you can extract them from the viewer and you can save them in your working spaces here. So we have an example of one of these already in this example that we've provided for you, which is this Ultra data description JSON. And if I open it, you can actually have a look and see what it looks like. And I'll expand it all now so you can see the different things in there. There you are. So this gives you all the information about what we're looking for. There's that data set ID. We've got a subsetted area. we've got a position in time, we've got a platform name, we've got a product type and a timeliness. And you can manually edit these things if you want, but it's actually usually the easiest thing to do is to copy it from the viewer when you've set up that first query using the clickable data catalog. You can also set up more complex workflows then where you may change this in a text-based way, which you can actually see we can do in some of the examples later on. But I've saved that example in here so we can run through this one to see. So in these cells here, what we're doing is loading those files. This example here. Oh, not found my one. Let me run it again. We can also then, I'll have to look at that in a second and see why it's not finding that, but we can also run the query and create it ourselves here. So basically you can either create it as a file and save it, or you could write it as a cell. Again, this is the kind of better practice approach. I'm not entirely sure why it's not working. I might have to rerun the notebook just to see if it can find it. But you can also set it manually, as we have in this example here. And then last but not least, we can actually run the API requests. So we can take all that information we've given the client, so our username and password and our request for the type of data we want, and run it. And then that should start downloading if we've done it right. And this is always the risk of doing a live demo. You really hope these things are going to work. Let's see. Give it a second. It's definitely doing something because you can see from this very helpful indicator up here that it's looking for its CPU is running. Okay, here you go. So you can see now that it's downloading. And if you were paying attention, then you'll have seen that a file appeared on the left in the browser over here. So that is the file that I was looking for, and it is downloading. In fact, I think it has already finished. So it's very quick because we're sat in the from the central place where it is into your working environment here for you. And so now we can work with that data. Unfortunately, this notebook doesn't do anything more than download. It just shows you what it is that you can do to access data in this way. But we have a follow-on session coming with Ben, who will show you a more thorough workflow that will show you how to download the data, but then also do some interesting things with it in Python. So I will stop there. If anybody has any questions, please do feel free to ask. I'm happy to go back and look again at any other bits and pieces from this notebook as well. I'm actually going to rerun this and just see if there's a problem with the JSON. So this time it loaded. I'm not sure why it didn't before, but as I said, always good to go back and maybe restart and run things in case you've missed a step or something like that. Okay. So do we have any questions? So we had the one about opening the Jupyter Hub, so I can actually show you that again. Go to WEkEO.eu. So once you sign in over here, you get your dashboard, click on that, and then you have Jupyter Hub, and that will automatically spin you up into the Jupyter Hub. Now, I already have an instance open, so it's gone straight to this. You'll see that you get two options, one for Earth Observation Hub and one for machine learning. If you're running some of our machine learning notebooks, you maybe want to use that because that's slightly different libraries installed and slightly different RAM and storage allowances. So, but otherwise, you can just use the top one. Okay. Any more questions at all? Where questions tend to come when you actually go and work with this. So, like I say, I'm happy for you guys to contact me or through WEkEO afterwards, and we can always go through this in more detail if you get stuck with anything. Otherwise, I think I can hand over to Ben. Are you online, Ben?
I am. I'm right here and was following along with your demonstration.
Great.
Just turn my camera on and close down the chat for a bit. Okay, so I guess we don't need to take any breaks or anything. We should just go straight into doing what we do. Okay, so let me just share my screen because, like Haley, I am not going to give any presentation today. I'm going to do absolutely everything as a live demonstration. And what I'm going to do today is build on what Haley showed you already. I will start at the very beginning and we'll spin up our WEkEO Jupyter Hub. We will clone in the code that we need, and then we are going to work on a notebook that looks at sea surface temperature data, both from EUMETSAT and from the CMEMS catalog, to look at marine heat waves. So I'm going to show you basically though how to access all of our code, and then we'll focus on one small part, and you should be able to, after this, look at any of our notebook data and see what applications or what satellite thematics are most interesting to you. So I'm just going to share my screen or find the right part to share. Okay, so you should just be looking at my Google homepage. I'm just going to make it a bit bigger so we can all see where we're going. Would like to get rid of that, but I don't know how I can. You seeing my screen share?
At the moment, I see your Google.
Yeah, you should just be seeing this, and I could just write whatever in here.
Yep.
Fantastic. Okay, so let's start by going to WEkEO.eu. So this is going to be our start point for our demonstration for today. Just out of interest, could you see when I type that in the bar, because it looks like you can only see the page and not the thing. So I'm just going to stop my sharing and reshare as whole screen, because otherwise you won't be able to see anything that's happening on the URL bar at the top, which is rather annoying. Okay, so now you should be able to see this bar at the top where I was typing. So we're going to go to WEkEO.eu. That brings us to our WEkEO front page. And the first thing we're going to do is just sign in to WEkEO. This should open up the following page, tell you your credentials, and then you click the big sign in button or add them as you require. And now I'm at the WEkEO front page, but instead I'm signed in. I can tell I'm signed in because it says sign out, and I'm going to go to my dashboard. And then from my dashboard, I'm going to go straight to this link on the left-hand side to Jupyter Hub. So this is exactly what Haley showed you how to do a minute ago. This will open a second window. And here I am inside Jupyter Hub. Now, I was working here a minute ago, so I've opened up in a terminal window, but I'm just going to close that, and you should see a view that looks exactly like this. So once you arrive here, you can see that I've already run the demonstration that Haley ran a minute ago, because I've already cloned this WEkEO for data repository, and I've already set up this myconfig.txt file that I'm going to use a little bit later on. So I am exactly where Haley left things before. And what we're going to do now, though, is we are going to add all of our ocean training code to our environment. So the first thing we want to make sure is that we are in this kind of base level folder. So you should be able to see a folder called public in here. Now, inside public is where all of the pre-existing copies of all of the data relevant to ocean, atmosphere, climate, land, machine learning all reside. But those are all read-only options, so we're not going to go near those right now because we actually want to do a little bit of editing with our code before we start. So we'll go back to the top level, and we're here. I've already cloned in WEkEO for data, and we're going to clone in all of our ocean code, which is called WEkEO for oceans. So the first thing I'm going to do is I'm going to open this terminal window. Now I need to check that I'm in the same place as here, and for those of you who aren't used to working with the terminal, if I type pwd, it says present working directory. This tells me where I am. And if I type ls, this tells me what I can see, lists what's in the directory. And you can see that this list of stuff here, I can make it in a big list like this, corresponds with this list of stuff over here. And sometimes you can see a little bit of extra things like lost and found, but otherwise you can see myconfig.txt is here, old files, public, WEkEO for data. So now we know we're in the right place where we want to clone our repository to. But what repository are we going to aim at? We want the WEkEO for Oceans repository, and I can find this just by typing WEkEO space GitHub in my taskbar. It should be my top hit. And you should come to a page that looks like this. I will put this URL quickly in chat. Apologies, it'll go a little bit strange for you. But here is the URL to get the code. And in this page, on this list, I'm signed in, but you will see exactly the same thing as I do. If we click on repositories, we can see all 22 repositories that are currently available to clone in WEkEO. Now, some of them are actually wrapped up versions of others. So you can see if we scan down here for marine, we have one called Ocean Case Studies. We have ones called Learn SRAL, which is related to Sentinel-3 altimetry. Learn SLSTR for Sentinel-3 sea surface temperature sensor, which we will work with a bit today. Learn ALTCHI for ocean color data, and some other stuff related to various tools or various applications or activities that we've been involved in. Now, the one we're interested in is called WEkEO for Oceans. So I'm going to click on this. And actually, inside here, you can see that there are links to some of those repositories already inside this repository. This is something we call submoduling. So when we clone this WEkEO for Oceans repository, we will get all of these included, which is what we want. This will be the full catalog of ocean relevant notebooks for WEkEO in one go. So it tells you a little bit about the repository once we are in here, including, who wrote it, what are the licensing conditions, how do you use it, and most importantly, the README for how do I actually get this code to the place where I want to work. So I'll leave you to kind of read this at your leisure to find out more information. You can actually also find contact details on here for how you get more support in working with this data. But the key piece of information we need is this first grayed out piece of code. We can ignore this CD work and just copy this line. So I'm just going to copy this. And actually, I realize there's something, so I'm going to change slightly. But I'm going to paste this in here. And I'm just going to get rid of this remote submodules, because in this case, we don't have any remote submodules. And I will make sure I update the README to make it to fix that issue. So I'm going to type this one line. This is going to use our Git toolkit to clone, so make an identical linked copy of all of the code that's in here. And it's going to get all of the submodules that are buried inside this, including Learn ALTCHI, Learn SRAL, Learn SLSTR, and the one we'll work with today, which uses both EUMETSAT and Copernicus Marine Service data from Mercator, the Ocean Case Studies repository. So I click and off we go, and it will take not too much time. It'll take a bit more time when it gets to the case studies one, because I've already pre-populated it with a bit of data, so we can do some more stuff today than we would typically be able to cover. But you can see it's already done ALTCHI, it's done SLSTR, it's just doing SRAL now, and then it'll do case studies, and case studies will take slightly longer, but shouldn't be too long. And then it'll just go and get a couple of submodules that are buried within submodules until we've got absolutely everything. And you can see on the side here, we have WEkEO for Oceans in our nice readable, writable space. So what have we got? Let's look inside WEkEO for Oceans. We have everything we expect. We have Learn ALTCHI, SLSTR, SRAL, and our one of interest, Ocean Case Studies. Now, in the past year or so, Haley and myself and a load of other developers and training colleagues that work at EUMETSAT have been authoring some case studies that run alongside the UN Ocean Decade challenges. The UN Ocean Decade currently going until, I believe, 2030, but I might be correctable on this one. And so inside this repository, we have all of our notebooks that deal with data and applications that run alongside these UN Ocean Decade challenges. Now, in all of our notebook repositories, the most important thing to find in here is this little file called index. When we click on index, this will open our first Jupyter notebook, and this notebook is only provided as a guide to link you to all the other notebooks that are in this repository and give you the rationale and reasons for why we are doing what we are doing. So you can see here's my name up here, here's Haley, and here's a couple of our colleagues who work in altimetry and ocean color. And if you read a bit further down, it tells you a bit about the UN Ocean Decade and these ocean case studies, a bit more about how to use this material, what you're going to learn as you work your way through this compendium. And towards the bottom, links to the 4 notebooks that are currently in here that deal with specific tasks. So we have one on heat waves we're going to look at today. We have one that's focused off the in the Benguela upwelling system that looks at harmful algal blooms and deoxygenation. We have one that looks at carbon pools in the ocean, particulate organic and inorganic carbon. So again, it's focused more on blooms. And then we have one that looks at altimetry data and tracking tropical storms with altimetry. And all of these are linkable. So if I click on this link here, it will open the relevant notebook that is in this folder. So I'm going to go ahead and do that. So this is the notebook where we're going to be spending most of our time in the next half an hour or so. And I'm going to go through this relatively slowly and give you quite a fine-grained overview of what actually is happening as we run this notebook. So I think Haley is manning the chat and can interrupt me at any point if there are any relevant questions, because the way I'm running the screen share, I can't see the questions at the moment. So apologies if I miss a couple of things and have to come back. Try and make that slightly bigger. And I think, excuse me, go back to this one. Just going to try and close this sidebar because it just takes up far too much space on my screen and makes things confusing. Okay, so welcome to our Marine Heat Waves notebook. Hopefully some of you have managed to get this far. If not, I can give it a couple of minutes whilst I talk around the top part of this notebook here. There's another link back to the index file where we just were if you want to kind of toggle between working on different notebooks at the same time. You will find that these notebooks exist kind of in the wild, not just on WEkEO. We've provided a couple of little badges at the top here. If you happen to find these on our server, either GitHub or GitLab, you can just click these buttons and it should take you directly to the places where these notebooks run. So it should essentially spin this notebook up with a single click, and you can do the same thing on the remote binder system as well. I don't advise clicking them whilst we're in the context of this demonstration, as it will take you to an external service, and we're already where we need to be to run this anyway. So no problems, really. We are where we need to be. Okay, and then at the top of the notebook, the first thing we come to is a big orange box that tells us the prerequisites to or information that we either require or might want to know before we embark on this notebook itself. So the first thing that you will need is you will need a WEkEO account. So hopefully you all have one of those already. The next thing we link to is you might want to take a look at a series of notebooks that we have on how to work with the SLSTR. So that is the sea and land surface temperature radiometer on board the Sentinel-3 satellite. We have a bank of notebooks that tells you a bit more about how to work with this data, as it's what we call level 2, so it's relatively complicated. And the last thing here is a link to, and I'm going to follow this one, more information on this case study itself that we've published on the EUMETSAT website when we put this case study itself together back in summer 2022. So if you are interested in more information on marine heat waves beyond the one we're going to focus on today, then you can go and read through this case study, learn a bit more about what heat waves are, how we classify them, what they mean for the local biology, etc., coral reefs, and then a lot more information about how we observe sea surface temperature from space. And you will note that some of the pictures that we make in our notebook today are nearly the exact ones that we use on this case study, because actually we use this notebook to generate the images for this case study. So we give you the opportunity to recreate in this notebook this image, our climate stripes, and a heat wave test as well. So we're going to do 3 or 4 different plots today as we work through. Okay, so going back to the notebook, those are our prerequisites. That is everything we need to really do, and then we can sort of proceed through. Now, at the moment, I'm just going to skip forward a little bit, and you'll notice that we have little ones here, or little numbers. That means this notebook is already in a pre-run state, and we always distribute our notebooks in a pre-run state because then you can see all the nice pictures that are available within them. However, I don't want to do that. I don't want to just talk over it. I want to actually run it. So I'm going to go to kernel at the top, and I'm going to restart and clear all outputs. So that means all of these numbers are going to go away. And I'm going to start with something that is completely blank before we go any further. Okay. Now, the other thing that I'm going to do is I'm going to make sure that we are working in the right environment. So if we click towards the top here, we are working with an IPython kernel called Python 3. But if you remember yesterday from some of my demonstrations, I showed you about working with virtual environments. And inside here, we should find that we have 3 options available for this work. We have Python 3, Mini WEkEO and one that I've set up that you will all have access to called CMTS Ocean Case Studies. So I'm going to click on that one and select it. And all that means is I will now have access to all of the packages or Python packages that are installed in this environment, which I know has been set up to accommodate everything we need for this notebook. So once you've cleared your kernel and once you've chosen your environment, then we're ready to go and we can start proceeding through what we our notebook to look at data, sea surface temperature data from multiple different sources. So at the very top, I've told you what data we're going to use, and I've provided you with links to more information on these. We're going to look at the sea and land surface temperature radiometer level 2 sea surface temperature product, and we're going to look at the global Austia SST level 4 reprocessed product. Now, I'll spend a little bit of time telling you about these two. The SLSTR product is a level 2 product, which means it kind of comes directly off the satellite, and it has a coverage that's in a swath. We lose lots of data to cloud. We lose lots of data to places where we are unable to measure with confidence the sea surface temperature on the ground. And so we flag all that data and we throw it away. Now, there are advantages and disadvantages to this. Level 2, we're working very near to the fundamental levels that the satellite produces, which means we tend to have access to the highest possible resolution data, and we tend to be able to get it nearly instantaneously, or within 3 hours if we're working with near real-time data anyway. Now, the disadvantages are we tend to lose lots of data in terms of coverage, and a lot of the time you might not want to look at the instantaneous signal for the sea surface temperature. You might want to look at a time series for a much longer period, especially if you're trying to classify something like heat waves, where you need a climatology defined in order to be able to say what is the deviation or the anomaly from that climatology before you classify it as a heat wave. And that's where this Austia SST product comes in. Austia uses sea surface temperature data from multiple sources, including a large number of satellites, both microwave and infrared radiometers. So it has a much better coverage in terms of its kind of like the amount of data that is missing from it is significantly less. It goes much further back in time, but there is a cost in terms of the degradation of the resolution. It's not as high resolution as, say, the Sentinel-3 SLSTR product. So we're going to take a look at both because we can do some comparing, some contrasting, and paint some of a picture of why you would want to use different data sets for different things. Both of these data sets are available through WEkEO, and I've provided links to where you can find a bit more about them. The Sentinel-3 SLSTR product is actually provided by EUMETSAT, and I've got a link in here as well where you can learn a lot more information about that data if you're interested in working at the more fundamental satellite levels. So broadly, here are the steps we're going to go through. We're going to download some data. I'll come to that in a second. We're going to spatially plot some level 2 SLSTR data to get a high resolution look at the area over the Great Barrier Reef. And then we're going to download some Austia SST data to start to look at whether or not there are heat waves occurring in this region and when. And we'll do a couple of other little bits along the way. Now, I'm not going to read through all of the outline of the notebook, a little bit of background material for you to go through when you have a bit more time. I'm going to move straight on to our Python code. So when you work with Jupyter notebooks, anything that is in white is kind of contextual information, mostly just text or video or images, and anything that is gray is actual code itself. And in order to run code, we can click in the box, and you can either choose to click this play button, or I find much easier if you hold down Shift and hit Enter, then it will run. And now I have a 1, telling me this is the first piece of code that I have run inside this notebook since I reset the kernel. So I use a lot of packages in this notebook, but each one of those packages has a description telling you what it does. You can also, for example, I'm just going to write this and then delete it, but you can also put help, and then you can put the name of any package in here, for example, and then it will actually tell you a bit more about what that package does. Somebody yesterday asked how you know what packages do what. If you look at our notebooks, it will give you a little bit of an inkling as to what some of them do. which might be a good guide for seeing how you use them later. Okay, so these are all fairly standard available Python packages, but we're going to import one more, which is fairly specific. And this is a package developed by some, I believe, Australian researchers who actually have a Python package for detecting marine heat waves. And it's called this XMHW. So we're going to import that guy as well. So I put him separately just to kind of show you that there's a difference between, you know, standardized and fairly kind of bespoke or individual packages that we've got. Now, in the next directory, we've got, it only does one thing, sorry, next directory. In the next code cell, all this does is create two directories, one called products and one called pre-computed. Excuse me a sec. And inside these directories, we would usually store anything we downloaded in the products directory and anything we pre-compute, so anything that we need to kind of process on the fly in the pre-computed directory. And the reason I've set it up like this is if we were running this without kind of doing some on-the-fly processing, we would need about 3 GB of storage space to hold this. And that is really more data than we want to work with, and certainly more than we want to leave lying around. So I do a little bit of kind of like pre-processing of the data, which I'll tell you about in a sec. So all this would usually do is make these two products and pre-computed directories. Now, the reason I say would do is because it will do that if you have download data selected as true. Now, in order for us to get a bit further in this notebook and not spend 40 minutes watching data download, or actually a little bit less than that, quite a lot less than that in this case, I've set this to false. And if I just open the sidebar again, you should see that inside here, you already have a file called Ostia SST. And inside the pre-computed directory, you already have 2 granules from SLSTR. So I've essentially preloaded this environment with the data that you need. If you ever want to run this notebook with your own data to look at a different space, you can. You just have to set download data equal to true, and then to redefine the area and time series or times you want to look at in order to customize it as you see fit. But for the purposes of today, we're just going to work with the data we've got. So this download data is set to false, which kind of means that we're locked into looking at these regions, really, because that's the data that we've got. So just going to run this guy, and it's actually not going to do anything for the time being. But when we did acquire the data, it was over this region, which is just off the east coast of Australia. And then we have a smaller region that we extract because we're extracting for 30 years of daily data, the Ostia sea surface temperature data from the level 4 product. Okay. Now, below here, we have a kind of a bit of an aside, this orange box on supporting functions. Now, this is a fairly complicated little function that I've written, and a function is just a piece of code that you use repeatedly, but you want to be quite controlled. All this does is when I download the really quite large SLSTR data granules, it will cut them up and only extract the data for the area that I'm interested in. Just to have a small aside, if I just quickly open something else to show you, let me just hide this guy. So the sea surface temperature data from SLSTR often looks like these full swaths that cover an entire area. And we only really want, well, we're working off the coast of Australia, but we only want a very small part. So we don't want to keep this kind of full swath area. I can actually open, let me just quickly grab one other one. And you can open this data too through the WEkEO or my ocean viewers. But an example of a swath would be this full kind of area, and it actually will go all the way around the Arctic and down this side because it's actually a full orbit, and we only want a little bit. So all my piece of code here does is just cut out the small square we defined above. So it looks a bit complicated. You don't need to worry too much about it. All it does is a spatial extraction. Okay, and then we get to the first real task we want to perform, which is to download our data using the WEkEO HD8 adapter. Now, Haley's already shown you how to do this, so much of this should seem relatively familiar. But what we're going to do exactly before is we're going to define a configuration file with the data or with the information like Haley told you, so with the URL, your username, and your password. And then we're going to pass that to the Harmonized Data Access client in order to be able to access our data. Now, by default, it needs to be this HDArc file that is in the home directory. But you may have noticed that I've already set up one that's called my config. So if I just show you my sidebar again, go all the way back to here, I've got one called my config. So if I wanted to do this, I could set mine up as is shown here. And then I would just replace what was in here with the path to my config file. And I think in my case, that's something like, I can check. So there's my config, home, Ovian, which means Jupyter in Latin, and is always used on Jupyter hubs for some reason. I think it's Latin. My config.text. And now it should read my configuration information from that other file. And it's run through without complaining, so it's accepted that my configuration details are okay. So now I've authenticated the WEkEO HDA app with my my config file. That file could be literally anywhere on the system. You just have to give a path to where you'll find it. Okay, right then. So now we are authenticated. We want to go away and get the data that we need, and we're going to start with the data from the SLSTR data. I put in a screenshot here showing you how you can actually do some of this definition manually. If you're working on the WEkEO viewer, you can find the SLSTR level 2 sea surface temperature collection or layer, and you can actually put in some definitions here, your bounding boxes, north, south, east, and west, and your times. And if you click this Show API Request button, it will actually give you what we call the JSON configuration file you need to extract that data using code. So I could, have I got a bit of time? I've got a bit of time. We could maybe do this. So let's go back to WEkEO and then to data. And then I can look in here for SLSTR, for example, and I'm working with level 2 sea surface temperature. That's land, SST is here. So let's add this to my map. And you'll see some, oh, sorry, I just deleted it. You'll see the similarities with the other viewer I showed you. I probably should have shown you this one. I apologize for that. But now if we want to extract some data over a given area, sorry, oop, I will sign out. And hopefully give it a couple of seconds and it will load the metadata for this. Now I can define, let's say I want to define an area that goes from west of 140, south of -18, east of, let's just make that 145, 148, and then -16. I know that's areas over here. Alternatively, I could use this Set AOI button. Sorry, it's very small, but in the bottom right-hand side. And I can draw an area, and I can just copy my AOI from my map. And then I might want to say, okay, I want to look at, let's go for 2022, December. And I'm going to take roughly the same date because I don't want to look at too much data at the same time. And I can define if I only want data from Central A and B. There's only one product type, and I might only want NT data. So NT is non-time critical. That's the data that's had a bit more time to process and tends to be more accurate. And then if I do this Show API Request button, it will give me this JSON query file. And JSON is just the format. It's just a series of kind of nested brackets. This is the critical data I need for the Harmonized Data Access API to go and get this particular granules, or make this particular search for any granules that touch this square to load it into my code. So when I look a little bit further down here, you'll see that
Ben, you've muted yourself, I think, accidentally somehow there. I think when you clicked back, that's fine.
Hello, I'm back again. What was the last thing I said? Was you saw the WEkEO viewer part and then I came back here?
Yeah, go back to that bit. I think it was when you switched between the screens, you must have hit the mute button by accident.
Okay, but coming back to this.
There you go. Yeah.
Okay, good. Okay, so as I was saying, hopefully this won't happen again. This data that is available here is exactly the same as the data that I put in, or exactly the same form of data that I put in this query here. The only difference being these plot regions are what we defined at the top of the script, which just set my area of interest. So here is my query. My query is defined, tells me what data to get. Now we've selected download data as false, so no problem. But usually I'll be able to run this one and it would go away and say, in fact, because it's only going to do a little bit of a test, let's just have a sneaky edit on the fly. Don't worry about me. But this should go away and say, I found these two granules. Excuse me, I'll have a bit of water. So it found two SST granules that corresponded with my search, which is what I was expecting. And if I had download data as true, then it would now go through these, and this little part of the script would download these files, unzip them because they come as zipped directories, do my little bit of pre-processing to make sure I'm only keeping what I need over my small area, and then save them as new netcdf files inside the pre-computed directory, which I showed you already. So these two, which are around about 1 to 1.5 gigs each, get chopped down to about 45 megabytes for the area we want. So now we can kind of more easily work with them. Okay, so now we have our SLSTR data inside our pre-computed directory. We're going to go ahead and find them, load them in, and work with them to plot. So the next box in this script is just going to use this little library called glob, and glob just finds things for you. So it's going to look inside the pre-computed directory for anything that ends in NC, which hopefully should be 2 of our files. We can check. Let's actually just make a quick thing that says, I'm just going to say for, because it comes in a list, you can say for any item in the list, print that item. There we go. We found 2. So we found one from Sentinel-3A and one from Sentinel-3B. So great. We found the 2 files that we want. Fantastic so far. Now we're just going to plot those. So plotting is always the longest cell you ever have in any Jupyter notebook is the one that's geared towards plotting, because there are so many options you can choose with regards to things like color maps and font size and how you want to display it. So it's always a bit complicated. But trust me when I say that all of this stuff down here, all it does is make us a nice plot that should show up on the screen, should have coastlines added to it, and features and things like grid lines and axes labels, just so the map looks like it makes sense. And at the very end, it will make us a nice picture of our area. And let me just let me see if I can know where I can do this. I'm just going to zoom out a little bit for a while so you can see our really nice 1 kilometer resolution sea surface temperature mosaic across the western or eastern Australian coast. Eastern Australian coast. And this is at night time on December the 22nd, 2021. So this has actually just overlaid these 2 images, and you can see all kinds of interesting stuff happening oceanographically up and down the coast. There's usually a western boundary current, the East Australian coast, that kind of forms a little bit further south down here. And we end up with this really interesting kind of temperature gradient slightly to the north, where we have the influence of both the shelf and the wider Pacific Ocean. So this is usually an area that's relatively dynamic. It is a little bit less dynamic if we choose at night, because it tends to be a bit more quiescent, because we don't have the influence of solar heating. And that's actually the reason why for maximum quality data, we like to use sea surface temperature at night when we're working at level 2. So this is quality flagged nighttime dual view data from the Sentinel-3 SLSTR instrument, meaning it's already pretty good quality. But still, you can see we've lost all of this white stuff is either cloud or areas where we're not confident about the quality of the data that underlies it. So we've thrown this all away. This, in fact, is an extremely good example of a mosaic. You will find when you work with data at level 2, either for ocean color or sea surface temperature, infrared sea surface temperature, lots of data is nearly always missing. This is a particularly good example. We can see lots of nice stuff. This is an example of why you might want to use some of the level 2 data from the satellites kind of directly. You tend to get a lot more of that high spatial resolution. And because you're looking at a snapshot, sometimes it gives you a really good feeling for some of the features that you see, which when you move to levels like level 3 and level 4, where you combine lots of data together, tends to blur those out a little bit. So that data is very, very good for looking at different different features that might occur in a given region, but it's not very good at looking for data over time. Whilst it can be done, this is on an inconsistent grid with every single overpass, so it can become quite difficult to use this to look at any activity that involves looking through time series analysis, anomalies, etc. Fortunately, there are lots of researchers and processing houses who bring all of this level 2 data together to make level 3 and level 4 products that the Copernicus Marine Service produces and distributes, where a lot of this information has been, or a lot of these tasks have been done for you, because everything comes out at the end on a consistent grid you can easily grab the data from and do time series analysis on. So that's what we're going to move on to doing next. So moving on, the next thing we're going to do, if we were going to download it, is get the Ostia SST data from the Copernicus Marine Service. And you'll have a little read of this part when you have some time. It'll tell you a bit more about the limitations of the two data types, both the Sentinel-3 data and the Ostia data, with a focus on what we mean when we say reprocessed. So the data that we get from Ostia is our reprocessed data set, which means it is the highest quality that we can actually produce at the current time. Really, the only thing that would ever be higher quality in than a reprocessed data would be a CDR, a climate data record. And this is usually the long time series of data where statistically we've done everything to remove trends or biases or anything that could be an artifact of the data itself based on the length of the record. Traditionally, if we want to look at anything from a climate perspective, we need 30 years of data. Anything less than 30 years of data, then we start to see the influences of large-scale climate modes like ENSO interfering and giving us false trends. So we need to work with reprocessed data of the longest time series available to be able to look at any sort of climate impacts. And a heat wave is a climate impact. So if we really want to say categorically, this is a heat wave versus history, we need a lot of data to be able to do this. Unfortunately, we have that data in this record. We have Ostia data back to 1992. So we have the 30 years of data that we need in order to be able to look at whether or not some of the heat signals we saw above are related to marine heat waves. Now, gathering the Ostia data is very, very similar to getting the Sentinel-3 SLSTR data. Exactly the same kind of query is used. The only things that are different is we have different data set IDs, and there's a couple of small differences in the variables that we choose. In this case, it's called analyzed SST we want to get. So I can choose to run this query. We're not going to download it, but if we were, then we would just get this Ostia SST.nc file. I can hit go, but because download data is false, it's not going to do anything. But all this line in here does is construct this little data cube of all of the Ostia SST going back for 30 years on a daily basis for our region that we proposed. Just to look back up, I've proposed quite a small region to make this more manageable on a remote server. It's only a little box in here, 1 degree by 1 degree. But we are looking back 30 years of daily data. So I don't know who wants to do a back of the envelope calculation and tell me how many days that is, but it's around about 9,000, I think. It's quite a lot. So this can take some time to put all this data together in order to give you the full time series. And bear in mind that the server does not have unlimited capability. So if you request a large area or a very long time series, you might have to break this up into chunks so that you don't overload things and get a failed acquisition. Okay, now we've got our Ostia SST data ready. Let's start to do some work with it. So to prepare it, we're going to use a Python package called xarray. And this is a package that you'll almost certainly bump into in the first couple of months of working with Python. It's an extremely powerful way of opening mostly NetCDF files, but lots of different kinds of files, in a way that means you don't necessarily have to open it all at once. It will only go and get the little parts of the data as required. It can do lots of really interesting things statistically, such as taking means across different dimensions. It's very, very good at managing time series analysis, so you can group things into, for instance, years or create anomalies. And those are the two tasks that we're going to use it for here. So we've got this open MF data set, and this is just going to open our output file name, our ostia.sst.nc file. We're going to take a spatial average, a really simple one. We're not going to factor in the size of the grid or anything. We're just going to take a mean across latitude and a mean across longitude. That's going to give us a one-dimensional time series across the whole area. And then we're going to calculate annual values. So we're going to group the data basically by year and then take a mean across the time. So we'll get a single annual value. And then we're going to calculate an anomaly by taking that value away from every single other value, giving us the anomaly against the climatological mean across the entire series. Done. Simple, quick. X-rays are very, very fast. Okay. What do we want to do with it next? We're going to manipulate the data slightly because we're going to show it in a slightly different way that might be similar to you, and the title above kind of gives it away. We're going to make climate stripes for this area to see what we've got. So all I've done is I've taken our one-dimensional time series, our anomalies, and made it two-dimensional artificially so we can plot it in a way that looks like this. So welcome to the climate stripes for our 1 degree by 1 degree region off the east coast of Australia. And what can we see? Something fairly stark, that 2022 is an extremely high anomaly year. In fact, I think it's one of the warmest that's been recorded. 2020 and 2021 were notably warm years across the Great Barrier Reef, but for the area that we've chosen, 2022 was extremely warm. So we have an anomaly that's over 1.5 degrees warmer than the climatological average would have been. And if you look at this picture going back from 1992, you can clearly see that since 2016, it has been notably warmer in this region, or the occurrence of kind of anomalous warm periods are, well, 2 in 7, so making it a little bit more common than we would like. So this is a nice, easy way of showing in kind of like in one go what the temperature signal has been like in this region, and it is, to be honest, rather alarming. But let's take a look at the data in a little bit more detail. We're going to now take this same time series and we're going to subject it to our test for marine heat waves. So we're going to do a little bit of manipulation of the time variables that we've got. And the only reason we're going to do this is because it makes it possible for us to plot the dates along the bottom of our final plot. So all of this box, all it does is it takes the time that exists in our data set and it turns it into dates. You'll come to learn that working with latitude and longitude is really easy, and working with time is usually really horrible. Unfortunately, this is true across nearly all programming languages, but there's no universally agreed way of working with time or universally agreed way of displaying it. So it can take a little bit of well, slight annoyance, if you like, in trying to solve this small problem. Now we get kind of right down to our marine heat wave analysis. So we take our time series, and at the moment our time series is in degrees Kelvin. All we're going to do is load in our one variable, our analyzed SST, and we're going to take away 273.15 and convert it to degrees Celsius. And then this method threshold is one that's included inside the time series library or package that the marine heatwave package that we imported at the top of this notebook. And this is going to make a climatology from all of this sea surface temperature data. And after this, it's going to go away and look for the heat waves that it can detect by comparing the sea surface temperature climatology and the sea surface temperature signal itself. Off we go. Okay, so now we have our heat waves identified. Let's plot up some of our data, and we're going to focus on event 0, so the most recent event. It says in this time period of 30 years, it has found 58 heat waves. And we're going to look with this plot at the most recent ones for the 2022 period. And actually, that doesn't really fit on my screen, so let me try. So here we are. So here's a look at what the day-by-day breakdown looks like for the sea surface temperature over our 1 degree box off the east coast of Australia. And we can actually see through much of the summer, or southern hemisphere summer, because here is January of 2022, we were anomalously warm across this area. So we had significant numbers of heat waves that were occurring. The reason this one doesn't show, by the way, is just because we focused on the most recent one. So we can see all of this period here. This was warmer than the expected threshold that would qualify as a marine heat wave. So all of this warmer than we want, warmer than we would expect. And this blue line is the seasonal climatology. So you can see since 1992, the seasonal climatology, you can see how much warmer we are in general. So nearly always warmer than the 1992 to 2022 average. So that's the end of this notebook, and just an example of the sort of kind of multi-data set application you can work towards when you have access to all of the data sets on WEkEO. You have access to some data sets that gives you near instantaneous, or certainly available less than 3 hours in near real time. Data sets that show you features or high resolution areas of interest you might want to look at around specific events. But you can also usually find the corollary data sets that let you look much further back in time to give you context about whether or not what you're seeing is something that is part of a normal seasonal cycle, or maybe slightly anomalous, or really outside of the realms of what we really would expect or want to see, as is the case in this heat wave example. So that was my run through the notebook. I think we got some time left, and I've got a load more notebooks to show, but perhaps here it's best if we stop for some questions if anybody wants to know anything specific about what I've shown.
I think Haley was answering a couple of questions in the chat section. If you could just briefly go through some of those questions, so those who are not following in the chat section could also have a fair idea of how to deal with this. You have a great tag team partner already in Haley, so I'd leave you to it.
Ben, you're muted again.
I'm going to stop my share because you're staring at my team screen, which is boring, but I can go back to the notebook as required.
I can read some of the questions out to you if you like, Ben. So there was a question about, is it possible to demonstrate similar information for offshore West Africa? So I was saying for this that, and I think Ben, you can point to some of the bits in the notebook that things you would need to change. So the great thing about these workflows is that you can really apply them to most anywhere where the data exists. And for things like SLSTR and for the global Ostia product we're looking at here, they have global coverage. So the notebook is an example for an event that happened last year in the Great Barrier Reef, but there's no reason you can't apply this same analysis to anywhere you'd like. You just have to change a few things. So Ben, maybe you want to point out a couple of bits actually in here where that would need changing. So obviously the download, but then maybe some of the other bits as well.
In fact, very little of it needs changing. I would go as far as to say that the only bit you really need to change is this part at the top. So I have told my SLSTR search to look over this box, which is East Coast of Australia. And I have told my Ostia time series analysis to look over a smaller part of this box. You could change both these boxes to a region of West Africa, and that should be mostly it. I have deliberately chosen this region because I know I've got two nice SLSTR granules that fall on that area. So it might take a bit of trial and error to find nice granules that look at this sort of picture. But the Ostia product should be robust irrespective of geography. So you should be able to look at any area you want just by changing this. So it should be quite simple to reuse this notebook for any geography.
Okay, great. So one of the other questions, sorry, I'm just scrolling back up here. Yeah, we had a related question saying, does one always have to work in a larger area like Africa, or can this be done for specific areas, e.g. the western region of Ghana within a country and achieve the same good result? So I said here that this is kind of up to you as to how broadly you apply the analysis, but you might want to keep in mind just the general scale of the phenomena that you're looking at here. So marine heat waves occur I guess at relatively large scales, where we're having regional kind of climate activities. And you may have seen the blob, which was the famous marine heat wave off the coast of the Pacific, North America, that happened a while ago. So they can be quite big, but maybe not as big as a whole continent. So actually kind of the region you're recommending is probably a good size to have a look at. The risk you run if you look at too large an area is that if you conduct the analysis that Ben showed at the end, where you're doing like an average kind of over an area, you might smear out any signal that's there from the heat wave if you've got, a mix of cold and warm waters. So you kind of have to consider. You could also apply this analysis on kind of a pixel by pixel basis over time. So that would be a nice way to enhance this notebook. And I've seen that done as well. So yeah, you have to think about what the phenomena is, like what scale is it looking at to choose the right scale. Ben, do you want to add anything to that?
Yeah, I would do. I think you're absolutely right, Hayley. If I wanted to run this at the scale of, let's say, the entire Northern Pacific, then chances are it would all smear out. I am running this over a 1 degree by 1 degree box. That is 100 kilometers by 100 kilometers. That is kind of small. So I'm running it with this size of area just for the purposes of demonstration and not making you have a 200 megabyte file to copy inside this directory when you clone it. But when I ran this for the case study that you'll link to, I ran it over a significantly larger area to detect that this was a robust phenomenon. It's a well-documented one in this case, but I would be a bit wary about looking for heat waves in very, very small areas because it's just, there are some other physically oceanographic reasons why this might occur at small areas. So yes, but you can scale it up. You might have to change how you do your acquisition of the Ostia product, but you could do it for the whole world if you wanted to on a pixel by pixel basis.
Might require a little bit more space and memory than our JupyterLab has, but this is a good opportunity to say, you can always get a VM to do this kind of work with more resource. But yeah, think about your scale, think about the size of the folder, the files, stuff like that. There was another question then saying, are there other ways to import data to the Jupyter directly other than making a query? So I said here, like, you can actually load data manually in this. I mean, you can, I think it's under file in the Jupyter JupyterLab environment there, you can actually upload a file. But I would say if you do this, it's going to take you a very long time. So for example, if you went to the viewer, clicked to download to your local computer, and then tried to load it back up into the Jupyter Hub, it's going to take you a very long time. It's not very efficient. So using these APIs internally to the system is the fastest way to access this large amount of data. But if you had a small file with points in from, say, an in situ field campaign you've done and you wanted to load them in, you could. That's quite an easy thing to do. Other than that, I would say many other data repositories now have these API approaches as well. So you can probably make a call to them to bring the data in. Say you're working with things like Argo floats or something like that. A lot of those data stores have an API as well, and you can call them into this computing environment just as you would anything else. So Ben, do you want to add anything else on that?
No, just to agree with you, I will confess that I am less than 5 kilometers from EUMETSAT, being sat here right now. If I try to download the data to my local laptop over my pretty fast internet connection, it is not as fast as getting it straight onto WEkEO. So there is definitely some trade-off to be had with regards to the convenience of doing it through the GUI versus the speed of the download and nearly always the 10 times slower upload of data to any remote server.
Yeah, so I can tell you that, I mean, if you look at the top bar of Ben's screen here, it says Jupyter Hub WEkEO.apps.eumetsat.dpi. And what this tells you is that this computing infrastructure is actually based at EUMETSAT, which is where the SLSTR data, for example, also is. But we also have particularly fast internet connections set up between where this is and all the other data storage facilities in the WEkEO network as well. So it is much quicker for you to access all this data through here, which is definitely one of the pluses of working with the system. But it's a really great question, so thank you for asking. There was then another question, what do we also find in the config file beside the username and password? It's very simple. I think, Ben, if you scroll to the top of this notebook, it shows the thing I copied into the chat as well, which is just the, all you literally need is the URL, your username and your password. Here are. So it's very simple. It's a very boring little text file, but quite powerful. So you just copy paste that into a text file, which you can create just by right clicking or using the launcher to create the text file. And you only have to do that once. Once that's set up, you don't have to do that again. it'll call the same credentials in multiple notebooks when you make different queries. Ben, any more on that one? Want to say? No, pretty simple. And then what else do we have here? Ruth had a question. How do you export the information as a map with legends, north arrows, titles, scales, grids into a JPEG or PDF for display or printout? So Ben, can you maybe go back to that section of the code?
I can. I think someone else already asked this, but I'm also going to open the sidebar again because you can see it. So all of that is done by this one little bit at the end here saying plot save fig. So this by default will print all of this lovely figure out to my screen, but I've also decided to print it using this save fig as a PNG. So I don't know how Jupyter will do this, but there is the PNG file of that actual plot. So you'll be able to download this afterwards and export it as you wish.
Yep, and so you can see we've already got a scale on there, and we've got some latitude, longitude, and grid lines. And you can see, Ben, if you go back to the plotting code, you can see that those adding those features is individual lines in the plotting script. But you can do many more things using these plotting libraries. Python has extensive libraries that will allow you to plot in different ways, even interactively and things like that. It's really quite cool. You can do lots and lots of different things. Yeah, you can see here adding the coastline, adding different features, drawing grid lines, these kind of things. There's many more options on there. You could dig into the I think this is partly Matplotlib and partly Cart2Py, right, Ben? So if you look at those two libraries, you can find many more things that you could add. But Ben particularly likes doing this, so I mean, he makes much better plots than I do. Maybe he has some particular packages to recommend or things that are nice.
90% of what I do is Matplotlib and Cart2Py. If you do want to expose or export your plots to an external server, I really recommend a package called Plotly. And if you want something that's interactive on the screen that you can kind of scroll around a little bit, there's another really nice package called WEkEO, B-O-K-E-H. Those will be the three that I would recommend. I will put these in chat.
Great, thanks, Ben. Somebody asked, John asked, can I have the notebook after the presentation, please? You can have it right now. It's on the GitHub. I've dropped the link in the chat for you, so you can go and clone it to your local computer, download it, whatever you like. It's also available still in the Jupyter Hub in the public folder, so it's there for you to use already. Garda added a question. The memory shown in the top concerns all we are using in the directory or just the notebook where we're working on? I think if you're running multiple notebooks, it will show all of them. I'm not sure. Ben, have you tested that? If you run multiple notebooks at the same time?
Yeah, it's a really good question. And it's a question you're probably going to have to, it's going to be relevant for the entire of your programming career. So locally, you're constrained by just the specifics of your own computer system. But when you work on a remote cloud infrastructure, then you usually have to share this with a number of other users. So there are two memory icons or two memory bars in the top right-hand corner. It's a good spot. CPU, obviously, I think I'm highlighting it, is the one that tells you, your RAM, how much is running at the moment. This is usually your major limitation when working remotely. I think most virtual machines will have something like between 2 and 4 gigabytes of RAM available. And then you have another bar that tells you the actual storage space that you have. And this is usually much less restrictive. In which case, I've got 14 gigabytes. This memory bar on the right-hand side, it definitely reflects your entire system like allocation. And the CPU, if you're running multiple notebooks, will also affect your entire allocation. Learning to see, for example, I'm not doing anything here, but some stuff is happening on the system somewhere, either some sort of cleanup or something, and you may have seen that jumped to 20% temporarily. So learning to code to stay under this threshold is kind of a good exercise in good coding, and it's also why I do a lot of the stuff about chopping down data that I do, because I found out 3 days ago that running this on the on one remote server just wouldn't work at all. So I had to redesign the notebook flow slightly.
Okay, thanks, Ben. We have a question from Urias here. Are the data acquired by these satellites indirectly correlated with the impact on the ecosystem biodiversity of the region? What would be a specific scenario? So I guess if you're asking here about the marine heatwave example specifically, then yes, absolutely. And not even indirectly, pretty directly in a lot of cases. So what we're showing here is an indicator of thermal stress. So we can measure the SST each day and we can say how long it's above a certain threshold. And then we can use that to correlate with what's going on in the water in terms of biodiversity and ecosystem response. And one of the prime examples of this, if you look at the case study, which Ben is showing now, is a coral reef response. So coral reefs have this exactly as in this image here. They have a symbiotic relationship. When the temperature is over a certain threshold for a certain amount of time, it can cause them to be stressed. And they can then release these symbiotic algae and they become bleached and they turn white, which, you know, is not great for them. It means effectively they're dead. It's also not great for all the different species that are dependent on the corals for the services they provide to other species, and also for us because we like to go diving and see them. It's important for tourism. So there's a very direct link here. And it's not just corals that could be affected by heat waves. Other species can also be affected by these changes in temperature. There's some really nice references in this case study to look at all the different impacts of marine heat waves. So I would definitely recommend you have a look at that if you're interested in this particular thing. But generally, this applies for almost all the satellite products that we're talking about here. Usually all of them have a really strong motivation for why we're collecting that data. Lots and lots of different applications and links to effects on the planet. So yeah, nice question. Thank you. If you mean something different, please write in chat. We can address it again. And then we have a really great question from Quasi, which is, are we free to use these codes and resources in scientific publications? If yes, how do we cite them? Yes, please do use them. If you look in the GitHub files, you'll see that there's a thing in there called a license, and we have released all these materials under what is called an MIT license, which means you are free to reuse them as you like, really, almost, which is fantastic. We really like this approach. We want you to use the data as much as possible. So yeah, please do use them. If you do use them, let us know. You can email us and just tell us, hey, I used this for my study. Brilliant. And also, if you want to put an acknowledgement in your paper saying, you know, this was done using code from UMETSAT at this link, it's fine. They don't have a formal DOI or anything at this point. It may get to that, but we haven't got one at the moment. Ben, I don't know if you want to say anything more about licensing and citation.
No, free to use as you see fit for whatever purpose you want. Just let us know. The only thing I would say is this code is predominantly written from a training perspective. So the idea is we show you, nice ways of working with our data. There may be some other steps you might want to take in terms of data quality control before you want to publish on anything like this. So stay in touch with us if you're planning on working using some of this code, and we can maybe advise about some extra things you might want to do that just aren't really compatible with a kind of a training demonstration. Happy to help with that.
Yeah, we're definitely more than happy to collaborate and advise on these kind of workflows. It's happened quite a few times from training events. So we're open to that, and WEkEO is open to that. If you see something from one of these trainings you're keen and you want to, set up a temporary virtual machine or something to try some stuff out, let us know. We really want to help you develop your use cases where we can. So, okay, I don't think there's any more questions or comments in the chat. So if anybody does have any more, now is the time to add them. Ben, anything more you want to add on to any of those?
I could just quickly show the other 3 repositories and how you get the data for running all the stuff that's in there.
Yeah, sounds good.
Okay, so if you'll bear with me a second, if we go back to the start of where we were before, let me just put my sidebar on. We began and we had this whole WEkEO for Oceans folder, and we looked in ocean case studies. There are also 3 other repositories in here for working with the 3 sensors from Sentinel-3. If I choose Learn AltSheet, the ocean land color instrument, as an example, as before, we have an index file, and that will link out to all of the notebooks that we have that are relevant to ocean color. And there are more in this case, quite a lot more. In fact, I think through all the repositories, there's like another 30 odd. The most important ones for you will be these 1.1b, and I'm just in the index file now, because this will tell you how to get all of the data you need to run everything else in the introductory section of this notebook. So in all of these repositories under 1.1b will be a notebook that tells you how to get all of this data using the WEkEO HDA. We'll tell you a bit about the HDA itself and a bit about the WEkEO platform itself, and we'll fetch all the data that you then need to run 1.2, 3, 4, 5, 6, and 7. So once you've run 1.1b, you can run the rest of these if you're interested in learning about ocean color. Similarly, under the Learn SLSTR, the data that we use today, the sea and land surface temperature radiometer, exactly the same setup. You run this one. If you're working on WEkEO, you can work with the rest of the ones here. And if you're interested in working with altimetry data, the same thing under Learn SRAL. On this guy, you can work with the rest of these if you want to look at altimetry tracks, waveforms, sea surface height, significant wave height, and wind speed. So there'll be some on here that aren't really quite so WEkEO specific, but if you start with the 1.1bs, the rest of the introductory notebooks will be open to you to work with. So I encourage you to have a little look at those as well as the ocean case studies ones. Should point out the SRAL one also uses some Siemens altimetry, level 4 altimetry data. If you look at the sea surface height anomalies notebook, it will do some comparisons with a long track altimetry and gridded level 4 altimetry products. That's it. It's the only other thing I'll point out. Someone said the screen is not changing. Did that actually work?
I can currently see the index of the SRAL one. Did you move between others? Maybe it's just frozen for this person. For
I opened the 3 index files. That was all. That was all I did.
Yeah, no, I can see them. So I think it's just slow. But
okay.
We'll share, of course, a recording of this one. So if there's anything, if you've had any problems with the screen, I know sometimes it's a lot with the screen moving. You can always look back at those later with the recording. It should be captured, so that should be fine. Okay, a question from Garda. How can we use the WEkEO virtual machines? Yeah, so you can request these. You can look on the website. There is more information about the different sizes of virtual machine that are available. And depending on the size you're interested in, you get a shorter or longer free use period to try them out and have a go with them. Otherwise, it becomes a paid offering, although if you have got a particular use case, you can write to us and tell us what the use case is. And often we're able to support you for, slightly longer. We're quite flexible with how we offer support in these cases. So yeah, in short, have a look on the website. You can apply for one of the existing offers or drop us an email with your use case and we'll talk to you directly about what we can offer you that best suits your needs for virtual machine usage. A good question. Thank you. I'm glad somebody's interested in them as well. Okay, if there's no more questions, then I guess we can hand back to Ignatius to wrap up the week. Ignatius, are you there?
Yes, I'm here, Haley. Just a quick one before we wrap up. I've been receiving a lot of emails so far concerning challenges that some people might have been having with the AUC, GMS in Africa digital learning platform. So I just use this period to quickly go through the DLP and let people know how they can access the information and even some of the recordings that have been done so far. So I'm sharing my screen now. Upon logging into the AUC Digital Learning Platform, this should be your screen. If you're unable to find the course, just search it in the search bar and just type out Monitoring of Ocean Variables UOG, and it should bring you to this page. It's been created into different sections with general information, which should be able to give you all the announcements and all the discussions that have been taken on so far. And once you're done, completed the course by 28th February, you should be able to receive your certificate. The next session, we're looking at information on the GMS in Africa project. I have embedded some videos, so you should be able to watch directly within this window and information on the project in West Africa. There is a simple multiple choice quiz, 5 questions only. Just go through it, just make sure you're familiar with whatever has been taught so far. With regards to WEkEO, we already have some intro videos posted in here, again, by the same person, Haley. So it shouldn't be too difficult. You already have a face to put to the name, so you should be able to follow this. And I've also posted the live sessions from day one also in here. So it should be pretty easy to access. For those who are having difficulties accessing the link I sent yesterday, please just use the DLP. I'll be sending you another YouTube link and that should be easier to access as well. With regards to the second day, we should be able to get some information also on the Copernicus Marine Service and the My Ocean Pro viewer. There are lessons over here on how to register, search, and download information from there. At the bottom of the page also is yesterday. For today's session, everything will be posted in the last bit having to do with Earth observation data processing tools, the API that we just used. So everything, including the Jupyter notebooks, would be handled in the section as well. So I'd like to end here with this particular demonstration. I hope everything was captured, everything is well understood, and we should be able to go on with that. In case you have any problem at all, please just send me an email and we'll be glad to answer that. Before we end the session, I think we have about 15 minutes. I'd like to acknowledge all our trainers who have been with us from day one, from all the institutions. It's made it so easy. Some of these guys, all you have to do is just send an email, and actually they're just waiting for the opportunity to even render these trainings. As soon as you mention it, they're so nice and they want to come help you. So if you have any questions at all, please send an email from Fabrice to Fifi to Ben, Haley, and also Elena. There are a lot more people in the background who have been helping us with the training. And I'm sure even from UMETSAT, like Haley said, just send an email to ops@umetsat.int, and I think they'll be glad to help you. There'll be extra information on how to reach them. I'll be posting them. Before I hand over the mic again, I'd like to thank everyone who has joined us for these sessions. Thank you very much for following through. I know it's not easy taking 2 hours each day to listen to people talk. Online trainings tend to be a little difficult, and it's very difficult to follow, but I've made the time to follow that. So for that, I'd like to thank you all. I'd like to give the floor back to our trainers in case they have any extra things that they want to do, and probably I'll break protocol a bit. And if there are any of the participants who actually wants to use their voice, I apologize again for muting you for all 3 days. If you have something to say to the trainers, I would be glad to open up your mic for you to make any comments that you want. So I think we'll go in this order: Fabrice, Fifi, Haley, and then Ben. I know we usually say ladies first, but I'll plead with Haley. Let Fabrice go first, and we'll go in that order. Thank you.
Thank you, Ignatius. It was a real pleasure to participate and to collaborate on this training. It was a very good session today, and very big thanks to Ben and Haley to have prepared all this huge material and fruitful for you guys, I hope. And I hope to see you perhaps to another workshop together with University of Ghana. And I was very pleased to share this moment with you all. Thank you, guys.
Thank you, Fabrice. Fifi?
Yeah, I have nothing more to say again, but just I want to thank everyone being here, attending this training, and hopefully I think we'll meet next time also on other training and workshop we are organizing. So see you.
Thank you very much, Fifi.
Yeah.
Ben, and then Haley.
Yeah, I just want to say thank you very much to everybody for coordinating and delivering and attending this training. It's been really interesting, and it's nice to talk to passionate ocean-focused people about what their applications interests may be in the future. I am easy to find, and I write lots of these training notebooks and do lots of these training events. So hunt me down, ask me questions. You know, I'll be happy to help, especially on the technical side of things. So look forward to talking with you all more at some point in the future, and hopefully, given the opportunity, maybe even face to face. Thanks very much.
Thank you very much, Ben. And Haley.
I've one more to say following all you guys. Well, thank you obviously to Ignatius and the Ghana team for organising this event. It's always a pleasure working with you all, and thank you for bringing such an interesting training together. It's nice that we are able to move on to some of these more advanced concepts in our training now. I mean, initially I think we were talking a few years ago just about the data, but now we're moving much more into really extensive usage so people can actually do things really with the data that are particularly scientific and meaningful. So it was a really great opportunity to do that this week. Thanks to everybody else for supporting and bringing all their expertise together, and particularly thanks to all the attendees. I've really enjoyed the questions. I know online training can be a bit dry. It's not the same as when you get to know each other in person, and I really wish we could all be together. But I really am impressed by clearly you've been paying attention with the excellent questions you've asked. So I hope this won't be the only time we speak to many of you. Do keep in touch with us, ask questions, share with us what you've been doing. We love hearing from you. So hopefully I'll see you again another time. Thank you.
Thank you very much, Haley. I'll give a chance to maybe one or two participants. Just raise your hand and I'll allow your mic so you can speak if you have any words. Whilst I'm waiting for that, I'd also like to encourage all of you to take part in the training evaluation. This is important for us to get some feedback. This helps us to plan for the trainings that we have planned for later in the year. We'll be keeping you updated on the upcoming trainings in case any of you might be interested in those trainings. And please don't forget to include anything that you find was necessary or missing on how we can also improve this training in the future. Thank you very much. In case there's, okay. I think that's Louise. Just give me a minute. Okay, Louise, you're free to speak. Just enable your microphone.
Thank you very much to everyone. It's so nice to meet you. Thank you for the interest sessions. I am from Central America, so this was a very wonderful time and very precious sessions. I would like to have more time because 3 days are too short for all of the topics, but amazing job to everyone, and thank you.
Thank you very much, Louise. And also, I just realized that because we had a lot of participants coming from different parts of the world, we are a bit biased towards the English speakers. Once again, we'll try as much as possible to make the content available where possible in French. Sorry, I wouldn't say other languages, in French. So at least a wider community can get access to some of this material as well. One more speaker, and then I think we can wrap up. Is there anyone else? Okay, I think there was a request for another photo session. And since we have, I think 10 more, I'd entreat all of you to turn on your cameras so we can have another group photograph just to end the session. We have just a minute. If we can all turn on our cameras, please. I don't want to take the photo before.
It's so good to see you. Finally.
Is that everyone? I think, yeah, we're expecting a couple more. 30 seconds if you want to get into the photo. Interesting. We're getting a lot of women in the background. That's nice to note as well. Okay, I apologize for the absence of a flash, but I can assure you that the photo has been taken. Thank you very much all for joining us in this session, and I hope to see you in upcoming trainings. Thank you all.
Thank you, Ignatius.
Thank you all.
Thank you. Bye-bye.
Bye.
Bye.
Bye.